Okay, so in section 11.9, we're gonna write functions as power series. Okay, so we're going to turn a function, some f of x, into a power series. The key power series that we're going to use here is our geometric. So to help us here, we need to first remember, what is the geometric? It's the series n equals 0 to infinity of a number that's starting that first term, a, times r to the n. How do I write this? This sums to a, the first term, divided by 1 minus r, that geometric ratio, the common ratio, and it only converges for absolute value of r less than 1. This is the geometric. You gotta know this. This is, kind of your bread and butter right here. Okay, so let's do an example here, all right? So I want to express 1 over, let's do, I don't know, let's just try something, right? Let's do 2 plus x cubed, okay, as the sum of a power series and find the interval of convergence. Okay, so how do we do this? Well, we got to go back to our geometric series. Okay, so geometric series works like this. I have to make my function, okay? I've got to make my function. I want to have what? I want to have some number divided by 1 minus some ratio, okay? Whatever that thing is, okay? So variable with some numbers in it, who knows what it is, right? That's what I want. Right now I have 1 over 2 plus x cubed, okay? Now, what am I good with? I have a number and I have a number here. That's perfectly fine, right? All I'm wanting to do is make sure I have a number there, okay? So that's good. What do I need to start working on? Well, I want a 1 here, but what do I have? I have a 2 there. So how do I get the 2 out? Okay, how do I get the 2 out? I'm going to factor the 2 out of this denominator. So I have 1 over 2, and then I have what's left? 1 plus, well, how do I factor a 2 when there's not a 2 there? I just divide through whatever there by 2, okay? So now what do I have? I have the 2 outside, but I don't want the 2 outside. I just want the 1 by itself. So what am I going to do? Okay, well, what I can do is I can pull this up to the numerator because it doesn't matter what the number is. I just want to make sure that it's up top. So what do I mean by that? I'm going to put the 1/2 up top, and then what do I have? I have 1 plus x cubed over 2. You guys see that? Okay, now we're almost home. We're almost home. We've got a number, right? And then we have 1, and we got 1. Okay, we're good. We're doing good. What do we need to do at this point? What do we need to do? Well, I want to have minus something, but right now I have plus something. Well, how do I turn addition into subtraction? I can add through subtraction by subtracting a negative, okay? So what do I mean by this? The 1/2 stays the same up top, and I have the 1 here. That's good. But instead of adding here, I'm going to subtract a negative. And when I subtract a negative, that's addition through subtraction, which is exactly what I want. I want a number over 1 minus something, right? Something, okay? So now, what does this tell me? This is a geometric n from 0 to infinity of what? it's the number, the a up top, which is 1/2, okay, times my something, which is negative x cubed squared raised to the n power, okay? That's my a r to the n, right? That's exactly what I'm looking for in my geometric series, right? So now I'm going to clean this up a little bit. I'm going to use some algebra here. Okay, I'm going to use some algebra here. And so this is what? This is series n equals 0 to infinity. It's 1/2 still by itself. But then I also have what? I have negative 1/2 times x cubed to the n, right? Now, if I have like a times b raised to the n power, this is a to the n times b to the n. That exponent transcends into the inside of our parentheses there with exponent laws. And so what does this become? This becomes negative 1/2 to the n, and then x cubed to the n right here. Okay, negative 1/2 is the same thing as negative 1 times 1/2. So we can run the property again, right? So I have the series n equals 0 to infinity. A 1/2, I've got one of those right there. I have a negative 1 to the n. I have another 1/2, but it's to the n power. And then what do I do when it's a power to a power? X to the a raised to the b. Power to a power, I multiply the exponent. So this becomes x to the 3n here, okay? And then I'm going to use algebra to help me simplify even further. If I use algebra to help me simplify further, what do I have? Well, this one is good, negative 1 to the n. But guess what, guys? I can combine these two because they have the same base. The same base, what do? I add the exponents, n plus 1, right here. Okay. And then I have x to the 3n. So that, my friends, is what the geometric series looks like here. Okay. So, and then what are we asked to do here? We're asked to figure out the interval of convergence. So interval of convergence, I need to look at this and run the ratio test on it. Okay, so I want to look at this and I want to run the ratio test on it. So the ratio test, what's the ratio test say? Limit as n goes to infinity of an plus 1 over an in absolute value. So what happens in absolute value? That sign switcher goes away, right? So limit as n goes to infinity. Now n plus 1, so this is all an, okay? But n plus 1 would be 1/2 to the n plus 1 is n plus 2. And then this would be x to the 3n plus 1, okay? Don't forget your parentheses there. And then over what? 1/2 to the n plus 1, x to the 3n, okay? All in absolute value. And so I take my limit as n goes to infinity. All right, what's going to happen here? These cancel. I have one extra copy of a 1/2 left up here. Okay, there's nothing left down there, just a 1. And then in the numerator, what is this piece equal? Well, just a little scratch work. This is x to the 3n plus 3, right? Distribute the 3n or the 3 into both of those terms there. So x to the 3n cancels with x to the 3n, but that leaves me an x cubed in the numerator. So the x cubed is in the numerator there, okay? All right, so now when I take that limit, okay, when I take the limit here, all these n's are eliminated. So the limit really doesn't do anything here in terms of n. It doesn't matter. I get x cubed over 2 in absolute value. And then I want that limit to be less than 1. Then the series converges absolutely. By the ratio test. So now I need to solve this. X cubed over 2 and 1. Multiply by 2, negative 2. X cubed, positive 2. Cube root everything, cube root everything. So my interval of convergence is between what? Negative cube root of 2 and positive cube root of 2. Okay, that's my interval of convergence right there. All right, so what you would do at this point, you could check the endpoints here. If you check the endpoints by plugging in, if you plug in the endpoint here, you're going to get 1. Now, if you plug in that into your series, n equals 0 to infinity, negative 1 to the n, series 1 half n plus 1, and then you plug in your cube root of 2 to the 3, that undoes that. So that's basically 2 to the n, right? So this gets me negative 1/2 n, and then this is really 1 over 2 to the n times 1 over 2, right? And then this here is 2 to the n. So these 2 to the n's cancel. And so really you're getting something that's going to diverge here. Okay, so if you plug in these endpoints, the endpoints diverge. All right, so same thing goes for the other way. Your limit as n goes to infinity of your an is not equal to 0, and by the divergence test, you can say that the series diverges at the endpoints. Okay, and so the interval of convergence is just this open interval between negative cube root of 2 and positive cube root of 2. Okay, maybe we should do one more. Really, this is just an exercise in algebra, as long as you know your trick. Okay, so maybe let's just do one more just to make sure. Say we had like x squared over 4 plus x cubed. Okay, so what do I want? I want something over 1 minus r, right? That's what I'm wanting. Okay, now what do I have right now? I've got x squared. That's not a number, so I'm going to pull that x squared out. So I have x squared times 1 over 4 plus x cubed. Now that's not quite exactly what I want. I want this number here to be 1. So I'm going to run the same game again. I'm going to factor the 4 out of both of those. So I have x squared over 4, right, times 1 over, well, when I factored the 4 out, I'm left with 1 plus x cubed over 4. Okay, and then the last thing I want to do is I want to make this a plus into a negative. Okay, so how do I do that? I've got my x squared over 4 times 1 over 1 minus a minus x cubed over 4. Okay, so that's what's going on there. All right, now let's see if we can't figure out how to do this. Okay, so what do I have here? I've got a geometric, okay? It's x squared over 4 times the series n from 0 to infinity. What's my first term? It's 1, right? It's 1. Okay, a is 1 here. And my geometric ratio here is negative x cubed over 4 raised to the n. Okay, so what can I do? I can bring this inside. I can treat this kind of like my first term. If I wanted to leave it up here, that'd be fine. Okay, this distributes into that whole sum. So this is n equals 0 to infinity. I can do that. Look, this is in terms of n. This is like a constant, right? It's just like my constant. It's my a here. Okay, and then this is the same as negative 1 times x cubed over 4 to the n. So algebraically simplify here. N equals 0 to infinity. I have x squared over 4. This is negative 1 to the n. And then this is what? Well, it's each part is raised to the n. So that's x cubed to the n over 4 to the n. Okay. So simplify again, some more. I have x squared. Well, let me write this negative 1 to the n first. And then I have x squared. And I also have a x to the 3n. Okay, that's in the numerator. In the denominator, I have a 4. And I have a 4 to the n. So can I combine here? Yes, I can. Same base, add the exponents. Negative 1 to the n. X to the 3n plus 2 divided by what? 4n to the n plus 1. Okay? So what is my series here? Written a little bit cleaner. It's negative 1 to the n over 4 to the n plus 1 times x to the 3n plus 2. Okay? This is the function x squared over 4 plus x cubed expressed as a power series. Now you can run through the test yourself, but what you're going to do when you run through the test yourself, you're going to work through and figure out, what the interval of convergence is. And I challenge you to see if you can get it. Okay? And this function right here is only equal to this series on that interval of convergence. So it's only defined on that interval of convergence. Domain is all x for which the series converges. So run the ratio test. Use ratio test to determine the interval of convergence. Okay? All right, guys. Good luck.